Okay, Assalamu alaikum everyone. I'm Abdul Cham. I'm a fourth year medical student, and inshallah, I'm going to be explaining this section about regulation of volume and ion concentration in ECF and ICF. Since this is a recorded session, please do not hesitate to contact me at any time if you have any questions regarding the lecture through my phone number or my email. And with that being said, let's get started. So these are the objectives of this session. First, I'm going to go over distribution of water in the body. Then I'm going to define osmolarity and tonicity. Then we're going to go over the 6 types of fluid shifts and how they're going to look like on a Darrow unit diagram. But first of all, total body water. Total body water is all the amount of water that you have in your body. And it can basically make up 60% of your total body weight. So an easy way to calculate your total body water is just by multiplying 0.6, which resembles the 60%, by your body weight. So let's say we have someone who weighs 100 kgs. We multiply 0.6, 100 kg by 100 kgs. They have a total of 60 kgs of total body water. Okay. This is a rough way to calculate total body water in the general population. There are some more specific ways to calculate it, but this is what you need to know for the sake of your exam. Okay. However, you need to know what factors can cause this total body water percentage to change in different people. So the first factor that's going to affect the percentage, which is 60% of total body water, is the body composition, or the amount of fat there is in the body. So the more fat there is, the less total body water there is. And why is that? That's because fat is going to metabolize water faster, and as a result, the amount of total body water is going to be lower. Okay, so the more fat there is in the body, the less total body water there is. The second factor is the gender. So males are going to have more total body water percentage than females. It's actually related to the first point, or the first factor, which is the amount of fat, because females normally have a higher fat percentage. They're going to have a lower total body water. So these are two factors. First one, the amount of fat or the body composition. The first one is the gender. And they're actually related because they both go back to the amount of fat there is in the body. The third factor is the age. Um, in newborns, the total body water is the highest, and as they grow up, the total body water is going to decrease. Okay, this is because they need to metabolize the water, and because they are also gaining fat. So three factors actually can be combined into one, which is the amount of fat there is in the body composition. More fat, less total body water. The gender, females normally have more fat than males, therefore they're gonna have less total body water. And as children grow up, they're gonna have more fat, and as a result, they're gonna have less total body water. Okay. Now TBW is distributed into over the body, and it's first divided into 3/3. 2/3 of those make up the intracellular fluid, as the name indicates, the fluid inside the cells. While 1/3 of those makes up extracellular fluid, which is the fluid outside the cells. Now, extracellular fluid is further distributed over into quarters. 3/4 of those make up the interstitial fluid, which is basically the fluid between the cells, such as the fat cells and the muscle cells. Okay. And 1/4 of those make up the plasma. The plasma, which is a part of the blood. Blood is made up of plasma and RBCs. This is the plasma compartment of the blood. It makes up 1/4 of the extracellular fluid. This is another image or another figure that I got from Ambos that shows the water distribution in numbers. So if you prefer this one over that one, you can use that too. Okay. So what is body water balance? So basically, when you lose water, your body wants to compensate for it. So it's gonna do some certain stuff that's gonna replenish the water that's lost. And when there is water overload, it's gonna do some stuff to lose water and bring back the normal levels back. Okay. So what are the factors that are gonna affect the body water balance? These are the 5 factors. The first one is thirst center, angiotensin 2, aldosterone, ADH, and AMP. So let's take, so actually the first 4 ones are Just a second. Okay, so the first four uh, are responsible for increasing the water in the body. So when you lose water or get dehydrated, this is when these factors are going to kick in. And the fifth one is responsible for losing water. So when you lose, so when you have water, volume overload, this is when AMP is going to work. Okay, so starting off with thirst center, as the name indicates, when you are dehydrated, when you go for an exercise and you sweat, you're gonna get thirsty, and this is going to stimulate you to drink. And when that happens, you're gonna just replenish the water that you lost in your exercise. Okay, easy. What about angiotensin 2? Angiotensin 2 has multiple functions in the body, but for the sake of this lecture, we're just gonna focus on one, which is stimulating the release of aldosterone from the adrenal gland. Okay. Um, So aldosterone goes into the kidneys and acts on the kidneys, and it's going to increase the absorption of Na and Cl. Okay, and when that happens, Na and Cl are going to be reabsorbed, and they're gonna pull water with them, and therefore water reabsorption is going to increase too. As for ADH is going to go to the collecting duct of the nephrons, and it's gonna go and it's gonna stimulate the insertion of this channel called aquaporin 2 on the surface of the cells of the collecting duct, facilitating the reabsorption of more water into the body, bringing back more water to the body. AMP, on the other hand, as I said, is kicks in when there is a volume overload, and it's going to go and cause an increase in excretion of Na and Cl. Okay, and it basically works opposite to aldosterone. So aldosterone increases the reabsorption, therefore increasing water reabsorption. But AMP goes and increases their excretion, and therefore water is going to be lost with them. Moving on to osmolarity. Osmolarity is basically made up of two factors: concentration of the solute in the solvent and the number of the particles of the solute. Concentration is simple. You have 1 mole of NaCl, which basically one NaCl, in 1 liter of water, and the concentration is going to be 1 mole in 1 liter of water. Okay, simple physics. What about the number of particles? The number of particles depends on how many particles does the solute, in our case, let's take NaCl as an example, dissociate to. So when NaCl dissolves, 1 mole of NaCl dissolves, it gives you one Na, one sodium, and one chloride, one Cl. And these are two particles, although it's 1 mole of NaCl. So the number of particles in this example is going to be 2 because it's NaCl. Let's try to calculate the osmolarity of 1 mole of NaCl in 1 liter of water. So the concentration is easy, 1 mole per liter. What about the number of particles? We said that NaCl dissociates into two particles. So the number of particles is going to be 2 osmoles per mole. 1 mole divides into 2 osmoles. 2 osmoles basically means two particles. So in this example, osmolarity is going to be concentration, which is 1 mole per liter, multiplied by 2 osmoles, which is the number of particles, giving you 2 osmoles per liter. This is the unit of measurement of osmolarity. What is osmosis? Osmosis is the passive movement of water through a semi-permeable membrane. Passive movement basically means that no energy is used and it happens on its own. Okay. A semi-permeable membrane is a membrane that allows the movement of water but does not allow the movement of any other solutes. Okay, so only water can move through this membrane. Let's try to make to take this definition into a figure. So we have this container that has water in it, and it has two compartments that are separated by a semi-permeable membrane. Okay, on the first compartment, you have a high concentration of a certain solute, let's say salt, okay, NaCl. But on the other compartment, you have a low concentration. And this is a semi-permeable membrane. Normally, what would happen is that salt is going to move from this side to this side and equalize the stuff. But this can't happen here because this membrane does not allow the movement of NaCl through it. So something else has to happen to equalize the difference in concentration. Um, so this side is going to have higher osmolarity. Why higher osmolarity? Because we said osmolarity depends on concentration, okay? Okay, on concentration. So when you have a higher concentration, you're going to have a higher osmolarity. Okay, so this compartment is going to have a higher osmolarity because it has a higher concentration. And as we said, concentration, sorry, osmolarity depends on concentration. So when you have a higher concentration here, this compartment is going to have higher osmolarity. While on the other hand, this compartment is going to have a lower osmolarity. Okay? Because NaCl cannot move from this side to this side to balance things out, something else has to happen. And in this case, water is going to move from the area of lower osmolarity to the area of the higher osmolarity. While it's doing that, the volume here is going to increase. And when volume here increases, the concentration is going to decrease, okay? Because concentration depends on what? The volume that the solute is in. So when water moves from the low osmolarity area to the area of higher osmolarity, the osmolarity here is going to decrease and the volume is going to increase. While on this side, as more water is lost, the volume is going to decrease and osmolarity is going to increase. This is a very important slide because I'm going to revisit this idea multiple times throughout the lecture. So please make sure that you understand this. I'm going to go over it one more last time just to make sure that everyone is on the same page. Again, we have a container that has a semi-permeable membrane in the middle and an area with low concentration and an area of higher concentration. Normally, this solute is going to move here and balance things out, but this is not going to happen here because this is a semi-permeable membrane that only allows the movement of water, okay? So instead, water is going to move from the area of low concentration to the area of the higher concentration to balance the difference in osmolarity, okay? Osmotic pressure. Uh, so I'm sorry for this image. It does not have the best quality, but it's good for explanation. So I'm gonna go over it. Okay. So this is just the same example as this one. We have two compartments, one with low osmolarity, one with higher osmolarity. And water is gonna move on from the area of low osmolarity to the area of the higher osmolarity. And volume here is going to increase, and volume here is going to decrease. We already explained all of this. Now, if you apply pressure to the area of the higher concentration or the higher osmolarity, you can prevent the shifting of water from this side to this side, okay? And this pressure that you apply is called the osmotic pressure. The osmotic pressure is the amount of pressure that you need to apply to the area or to the compartment of the higher concentration to prevent the shifting of fluid from the area of low concentration to the area of higher concentration, okay? One important thing that you need to know about osmotic pressure is that it's dependent on the number of particles here, not their weight, not their size, only their number, the number of particles. Okay, this is where the first part of the session ends. Please make sure that you already understand everything before this because what I'm going to explain after is going to be highly dependent on it. Okay? Effective osmotic pressure. This is different than osmotic pressure, okay? Because it's dependent on something called the reflection coefficient. This reflection coefficient basically resembles the permeability of the membrane to a certain solute, okay? So let's take this as an example. If you have a membrane that's totally impermeable to a substance, and there's a difference in concentration, um, as I said, normally what would happen is that this solute is just going to jump to the other side, but this can't happen here because this membrane does not allow that. So there's gonna be osmosis from this side to this side, okay? But the way I like to think about it is that uh, because this solute cannot move here, there's constant tension between the two sides, and the water has to resolve this tension. But in case this membrane is impermeable to a substance, this tension is at its highest, and therefore the reflection coefficient is 1. That's the maximum you could have. When this membrane is totally impermeable to a substance, the tension is at its highest, and the reflection coefficient is 1. Okay? What if this membrane allows the movement of the substance now? Such as urea. Urea can move freely across the cell membrane. And therefore, if you have a higher osmolarity here than here, it's just gonna jump to the other side and it's gonna balance things out. Okay? And in this case, there is no need for water to move. And bringing back the tension example, there is no tension between the two sides. The tension is 0. And in that case, there is no tension, and therefore the reflection coefficient equals 0. Okay? Um, what if a membrane is semi-permeable to a substance, allows it to move a little bit? In that case, the reflection coefficient is going to be somewhere between 0 and 1. This is all what you need to know. You don't know to go beyond that, okay? So if the membrane is totally impermeable to a substance, reflection coefficient is going to be 1. If a membrane is totally permeable to a substance, reflection coefficient is going to be 0. What if a membrane is partially permeable to a substance? Reflection coefficient is going to be somewhere between 0 and 1. What's iso, hypo, and hyperosmotic solutions? So the osmolarity of the blood or the plasma is somewhere between 280 and 300. Isoosmotic means it's a solution that has the same osmolarity as plasma, somewhere between 280 and 300. In general, isoosmotic is just two solutions that have the same osmolarity, but because we here care about the plasma osmolarity, isoosmotic is any solution that has similar osmolarity to plasma. What is hypo and hyperosmotic? Hypoosmotic is basically a solution that has osmolarity less than 280, and hyperosmotic is a solution that has more than 300. Okay, easy. Isoosmotic, same osmolarity. Hypoosmotic, less osmolarity. Hyperosmotic is a higher osmolarity. What is tonicity? Tonicity, as the definition is a measure of the ability of a solution to cause a change in cell shape by promoting osmotic flow. Basically, you have a container that has water in it, and you dumped an RBC into it. What is the ability of that solution to cause this RBC to change its shape only based on osmotic flow? This is gonna make more sense as I'm gonna explain. So if it doesn't make a lot of sense now, just bear with me. This tonicity is determined by the difference in concentration of non-penetrating solutes, and we're gonna know why in a couple of seconds. But for now, if you have two compartments that have the same concentration of the solute that cannot cross the membrane, they're called isotonic. Okay, they're called isotonic. Um, Isoosmotic is not the same as isotonic because you can have two isoosmotic solutions, but they don't have the same concentration of that solute that you are looking at right now, okay? But isotonic, they have the same concentration of that solute, okay, and the same osmolarity too. So in that case, if you have two isotonic solutions, there's gonna be no water movement between them. They are equal, okay? They are in equilibrium. They are good with each other. What if you have two compartments that have different concentration of a certain solute? That is when you are going to have movement of water, okay? Now, why did I say that this substance has to be non-penetrating solute? Because if you have a substance that can cross the membrane freely, and you have a difference in concentration between the two sides, again, that substance is just going to cross to the other side and equalize the stuff. And you won't have any water movement as a result of that. And applying that to the shape of the cell, because there is no water movement, the shape of the cell is not going to change. It's not going to have more water or less water, okay? And in that case, the reflective coefficient is going to be 0 because membrane is totally permeable to that substance, and tonicity as a result of that will be also 0, okay? So we can only use non-penetrating solutes because they keep the tension sort of, and you need to have water movement in that case. But if you have a solute that can cross the membrane freely, in that case you're going to have zero tonicity because everything is going to be balanced out by the movement of that solute. What's the effect of osmolarity or isotonicity on or tonicity on the cell shape? Let's say we have isotonic solution. So here, let's imagine this is salt and ACl, And here we have a similar concentration inside and outside of NaCl. And NaCl cannot cross the membrane anyways, okay? So if you have similar amount inside and outside, there is going to be no water movement between the two sides. There is no need for that. They are isotonic, okay? There is no tension between them. In that case, the cell volume is not going to change at all. When you put the cell in an isotonic solution that has the same osmolarity of it, there's going to be no effect on the cell volume. What if you put the cell in a solution that has lower osmolarity than it or lower tonicity? So this inside the cell, you can see a higher concentration of NaCl than outside, okay? In that case, we go back to the container example where fluid moves on from the area of low osmolarity to the area of the higher osmolarity, okay? So water here is going to move from outside to inside. And when that happens, the cell is going to swell, okay? From the area of the lower concentration here to the area of the higher concentration here. Just like this example right here, okay? Low concentration to higher concentration. Okay, let's go back. What if you put the cell in a solution that has a higher concentration than inside it? In that case, the water again is going to move from the area of low concentration to the area of the higher concentration and cause the cell to shrink. It's going to lose some of its water and it's going to shrink. This is a summary slide of the previous 3 slides. And again, you see the VIP sign. So this is going to be a very important slides as we move on with the lecture, with the session. So I'm going to go over it again. When you put the cell in a solution that has the same concentration of this non-penetrating solute, there's going to be no change in the cell volume. But when it has a higher concentration of this non-penetrating solute, so like a higher concentration here inside than outside, the water is going to move from outside to inside. What if you put the cell in a concentration that has a higher concentration of the solute, in a solution that has a higher concentration of the solute? Now there is the lower osmolarity is inside, and water is going to move from inside to outside, okay? Measuring fluid volume. So we discussed that total body water distributes into intracellular fluid and extracellular fluid, and then extracellular fluids divides into plasma and interstitial fluid. Now you want to measure the volume of each one of those compartments. Starting off with a simple physics formula that you guys took in high school, concentration equals amount over volume. For example, let's say we have this container it's 1 liter, okay? 1 liter of water. I don't know what's the amount of water here, but you just injected 10 milligrams of salt here, okay? You injected 10 milligrams of salt. Then you diluted it, so you stirred the pot, and now the salt is distributed equally across this water. You take a sample and you measure the concentration, okay? You already know the amount because you are the one who injected this salt into it in the first place, okay? So you measured it before injecting it, so like 10 milligrams or something. Then you stirred it and you measured the concentration. You took a sample and measured the concentration. Now the only thing that's missing is the volume, and this is what you want to calculate. So volume is going to equal concentration multiplied by the amount that you injected. How do you get the amount? You are the one who put it in the first place, so you know it before, you measure it before putting it. Concentration, you take a sample from the solution and take the concentration and calculate the concentration. Then you can find the volume based on those two findings. This is the same way we measure the amount of body fluid we have. And this method is called the indicator dilution method. The indicator in our case is the salt dilution because it gets diluted. And this is why this is how you measure the volume in this case, okay? So in order to use the indicator dilution method to calculate the fluid volumes in our body, we need to fulfill 3 criteria about that indicator, okay? So this indicator needs to fulfill 3 criteria. First one, it needs to evenly distribute in the compartment that you are aiming to measure. So if you want to measure total body water, you want to make sure that this indicator is going to go and distribute evenly across all the water in the body. Number 2, it needs not to leak from the compartment. So because if it leaks, it's going to affect the amount that's inside and you're going to have wrong calculations. And number 3, it needs not to be metabolized or excreted. Same concept because this is going to affect your calculations, okay? Now, let's say you want to calculate the amount of water, the volume of total body water. Okay, so this whole thing now. Other than those three criteria that the indicator needs to follow, there are some additional criteria that it needs to follow. One, it needs to evenly distribute in the ICF and ECF. So it needs to go both intracellularly and stay extracellularly. And based on that, it needs to be able to penetrate the plasma membranes because it cannot go intracellularly if it cannot penetrate the plasma membrane. So this is the main criteria for the total body water indicators. And there are a couple of indicators that follow this criteria, and these are heavy water, radioactive water, and antipyrine. Unfortunately, you have to memorize those, so you can't really skip them. Uh, but again, if you want to calculate total body water, this indicator needs to distribute evenly across ICF and ECF, and it needs to be able to penetrate the plasma to do so, the plasma membrane to do so. Okay, because intracellular fluid, it needs to be penetrate the membrane to reach it. Okay. What about if you are measuring extracellular fluid? So you injected a certain indicator into the bloodstream, and you only wanted to stay outside the cells, outside the cells, and measure extracellular fluid volume. So again, the first criteria is that it should evenly distribute in the ECF. So it should evenly distribute across the interstitial fluid and the plasma. And how is it going to reach? So injected into the veins, how is it going to reach the interstitial fluid outside the veins? It needs to be able to go through the capillary walls. Okay, this is how it's going to reach the interstitial fluid. But at the same time, you don't want it to go through the plasma membranes because that's when it's going to reach the intracellular fluid, and you don't want that. You only want to measure extracellular fluid. So first criteria, even distribution in extracellular fluid only. It can go through the capillary wall to reach the interstitium. And number three, it cannot penetrate through the plasma membrane so that it does not go to the intracellular fluid. Last but not least, and it's regarding the distribution in the plasma, it does not attach to RPCs and proteins. This is kind of similar to the idea that it cannot be leaking or it can't be metabolized, because this is also going to affect your measurements when you are going to measure the concentration. Okay. So the indicators that follow this criteria are radioactive sodium, inulin, mannitol, lothalamate, and thiosulfide ions. These indicators basically follow these criteria and can be used when you want to measure extracellular fluid volume. Last but not least is the plasma. So you inject a certain indicator into the veins, and you want it only to stay in the blood to measure only plasma. And that's going to be your only criteria for the case of plasma. It's going to be able to remain only in the circulation and does not leave the circulation. And also, it shouldn't be able to go into cells. It only remains outside cells, only in the bloodstream. And indicators that follow this criteria are albumin labeled by radioactive iodine and some certain dyes. Okay. Now we calculated three stuff. We calculated total body water, we calculated extracellular fluid, and we calculated plasma. But we still want to know intracellular fluid and interstitial fluid. From now on, it's going to be very simple, very easy, only simple math. Let's start off with intracellular fluid. So total body water is extracellular fluid plus intracellular fluid, right? And you already have total body water. We calculated it using one of those indicators. And we already know extracellular fluid because we used one of those indicators. Tamam? Now, total body water, you know it, and you know extracellular fluid. So intracellular fluid is going to be total body water minus the amount of extracellular fluid that you have. What about the interstitial fluid? So you already know extracellular fluid and you already know the plasma. So you are going to just extracellular fluid minus plasma is going to give you the amount of interstitial fluid that you have. Simple math, okay? And these are the two rules that you can use to calculate intracellular fluid and interstitial fluid when you have these three compartments. Okay, now the second part of the session is over, and but this time I have a question to you. If you have an osmolality of extracellular fluid of 350 milliosmoles, while inside it's 290, what effect is that going to have on the volume of the cells? This is again related to the pictures that I explained about the shape change of RBCs. So here you have a higher osmolarity outside the cells and than inside the cells. I'm gonna give you a couple of seconds to try to think about it. Since it's a recorded session, you can just pause the video and answer it. But the answer is, in this example, is going to be B. Again, when you have a higher osmolarity outside than inside, the water is going to move from the area of lower concentration to the area of higher concentration, and this is going to cause the cell to shrink. Okay. Now to the last part of this session, which are the Darrow unit diagrams. These diagrams are basically diagrams that show the relationship between the volume and the osmolarity of ICF, intracellular fluid, and ECF. So when you have an increase in volume, you're gonna have a horizontal increase in the boxes. So the blue box shows intracellular fluid and the green box shows extracellular fluid. So when you have fluid expansion or fluid increase, you're gonna have the graph is going to go wider because there is an increase in volume, and the x-axis is the one that shows the volume changes. The y-axis shows the osmolarity changes. So when you have an increase in osmolarity, you're going to see an increase in the height of the graph of the boxes, okay? Now, when you want to see changes in fluid regarding the Darrow unit diagrams, there are three rules that you need to know. First of all, extracellular fluid changes first, and then intracellular fluid changes as a result of that, okay? These are first one and two rules, okay? The first one rule is that extracellular fluid changes first. The second rule is that intracellular fluid is going to, changes are only going to be due to changes in extracellular fluid. Sometimes extracellular fluid can change, but no change in intracellular fluid happens. It's not necessary for intracellular fluid to change every single time. When ICF and ECF are isoosmolar, so they have the same osmolarity, they are at equilibrium and no water change is happening. There is no tension between them. Okay. Now, similar to those two rules, I made my own rules that are gonna help you solve any questions regarding these diagrams. The first one, if there is an isoosmotic contraction or expansion, only extracellular fluid will change. Contraction is basically a decrease in volume, and expansion is basically an increase in volume. So when you have either an isoosmotic contraction or expansion, only extracellular fluid will change. Okay. When you have a hyperosmotic extracellular fluid, the ICF is going to decrease. So when there's an increase in osmolarity in extracellular fluid, there's going to be a decrease in the volume of ICF. Again, this goes back to this question here, the one we just discussed. When you have a higher concentration outside than inside, the intracellular fluid is going to go outside and decrease inside. Similar to that, if you have a hypoosmotic extracellular fluid, there's going to be an increase in ICF and water is going to move inside the cells. Now let's see what are the fluid shifts that we have and what effect are they going to have on that Darrow unit diagram. Starting off with isoosmotic volume contraction, this happens in stuff like hemorrhage, diarrhea, and burning. In those cases, the fluid that's lost is isotonic. It's similar to the plasma osmolarity. Okay. And as a result of that, you're not going to see any changes. Again, as I said, isoosmotic changes. So, isoosmotic changes. So there's not going to be any change vertically because the vertical or the y-axis shows the change in osmolarity. So isoosmotic, no change in osmolarity. What about the changes in volume? So as I said, in any isoosmotic volume, and as isoosmotic volume change, the change is only going to affect the extracellular fluid, not the intracellular fluid. And in that case, you're going to see a contraction in extracellular fluid, but ICF is going to stay the same. That's why you're going to see that the green box, which shows the extracellular fluid, is going to shrink or become smaller, but the ICF is going to stay the same. When you have a decrease in blood volume, in general, you're going to see an increase in hematocrit, an increase in RBC count per unit volume, and an increase in protein concentration. So let's imagine you put a tablespoon in 2 liters in a 2 liter water bottle, but you then put that same water spoon in a cup of tea. When you are gonna look at it in the cup of tea, it's gonna look more concentrated than when you look at it in the 2 liters water bottle. That's basically the idea about this. When you have less fluid outside the cells or around the proteins or around the RBCs, they're gonna appear as if they are more. Actually, they are the same amount. Okay. Also, you're going to have a decrease in blood pressure. This is basically due to the hypovolemia that happens. And this makes sense. You're losing blood, you're losing water, you're losing electrolytes, and therefore you're going to have a decrease in blood pressure due to hypovolemia. Moving on to hyperosmotic volume contraction. This happens in examples like where water is lost more than salt, such as in sweat, fever, diabetes insipidus, where there's an increased urination of water, but the amount of salt that's lost is not the kind of the same. It's not equal, okay? So you're gonna have a hyperosmotic extracellular fluid, and that's gonna show as a vertical increase on the graph because osmolality is shown vertically, okay? As a vertical increase on the graph. Now, because the extracellular fluid has a higher osmolarity than the intracellular fluid, and as we said at the beginning of the lecture, the fluids move from the area of low concentration to the area of the higher concentration. This is going to happen here. And water is going to move from extracellular fluid, sorry, yeah, water is going to move from the intracellular fluid, from the area of lower osmolarity, to the extracellular fluid. And this is going to result in a decrease in intracellular fluid. Okay, so in this case, both extracellular fluid is going to decrease first, and then intracellular fluid is going to decrease as a result of the higher osmolarity in extracellular fluid. In this case, again, you're going to have an increase in RBCs and protein concentration because they are going to get more concentrated. You have less fluid around them. But this time, the hematocrit is going to stay the same. Why is the hematocrit going to stay the same? We said that here ICF is going to move in from inside the cells to the outside of the cells. So in case of RBCs, the RBCs are going to shrink as a result of that. Again, back to this figure. Here you have a hyperosmotic outside than inside. Water is going to move from inside to outside. And these RBCs are going to shrink now. Now, because they shrunk, the amount of volume that they're going to take is less, and they're going to appear as if they have the same hematocrit before the volume or the blood was lost. Okay. Again, there's going to be a decrease in blood pressure. Okay. For hypoosmotic volume contraction, this is going to be easier than hyperosmotic. Hyperosmotic is a little bit tricky because hematocrit stays the same. You need to know why. It is because the RBCs are going to shrink as a result of water moving outside from the cell. For hypoosmotic volume contraction, this happens in cases where you have adrenal insufficiency, so there's no aldosterone. In this case, overall volume is lost, but more salt is lost than water. So the osmolarity in the extracellular fluid is lower. And you can see that as a vertical decrease in the size of the boxes, okay? So they are going to be shorter. When you have lower osmolarity outside the cells than inside, and again, water moves from areas of low concentration to the areas of the higher concentration. The water is going to move from outside to the inside of the cells. And as a result of that, the intracellular fluid is going to increase. Okay, that's why you're going to see a horizontal increase in the size of ICF box. Okay. Again, like any contraction, you're going to have a decrease in blood volume. You're going to see an increase in RBC count, in protein concentration, and a decrease in blood pressure. The hematocrit here is going to increase, just like it happens in isoosmotic, okay? Like in any volume contraction. The hematocrit is going to increase. But what happens to the RBCs in this case? We said that fluid is going to move from outside to the inside of cells. So these RBCs are going to swell. This is not very significant regarding hematocrit because it's going to increase anyways in any contraction, okay, except in hyperosmotic contraction. But you need to know it that in case of hypoosmotic volume contraction, the RBCs are going to swell, okay, because water moves in from outside of the cells to the inside of the cells, from areas of lower osmolarity, hypoosmotic, ECF, to areas of the high osmolarity. Now, moving on to the volume expansions, again, isoosmotic is going to be very, very simple to explain. Uh, it's just basically when you have an IV line in one of the veins and you injected fluid into it, that's isotonic to the plasma. You're gonna see an expansion in the volume, so the extracellular fluid is going to increase. You're gonna see that as a horizontal expansion of the box. But again, it is isoosmotic, so there's no change in osmolarity. So there's not going to be any vertical increase in this example. And again, going back to my rule that I made, is that when you have an isoosmotic expansion, there's not going to be any change in ICF. Okay. In this case, you have an increase in volume, and hematocrit, RBCs, and proteins are going to appear as if they are diluted or they are less. Again, going back to the tablespoon of sugar, this is basically it. When you put that tablespoon in a cup of tea, then you put it in 2 liters of water, it's gonna appear as if it's less when you look at it in the 2 liters of water, although it's the same amount. Okay, this is basically the idea. You have more fluid, therefore these stuff are going to appear as if they are less. Also, there's going to be an increase in blood pressure due to the increase in the blood volume. For hyperosmotic volume expansion, this happens in cases where fluid that is hyperosmotic is injected, or in case you eat a lot of salt. So in that case, you're gonna have hyperosmolarity of the extracellular fluid, and this is going to be seen as an increase vertically in the osmolarity. Okay. Now, because there is higher osmolarity outside the cells than inside the cells, we go back to the picture here. Water is going to move from inside, from lower concentration to the higher concentration. In this example, water is going to move from extracellular fluid to the intracellular fluid. Okay. Sorry, from the intracellular fluid, from the areas of lower concentration to the areas of the higher concentration. ECF is hyperosmotic in this case. Okay. So as a result of that, the amount of the volume of ICF is going to decrease, while the amount of ECF is going to increase. So you're going to see a smaller a box that's smaller horizontally in the ICF, but ECF is going to increase. It's going to become larger. And both are going to go up because there's a hyperosmotic volume expansion. It's hyperosmotic, so there's an increase in osmolarity. In this case, just your typical blood increase in blood volume, we're going to have a decrease in hematocrit, a decrease in RBC count, and a decrease in protein concentration, in addition to an increase in blood pressure. What happens here is that ICF fluid is going to move from inside the cells to outside the cells. So what effect is that going to have on the RBCs? They're going to shrink, okay? The water is going to diffuse out of the cells, and RBCs are going to shrink. This is not going to be significant because the hematocrit is going to decrease anyways, even if they did not shrink, okay? Last but not least is hypoosmotic volume expansion. So this happens in cases such as SIADH, where this is just a disease where there's an increased excretion of ADH. As a result of that, you're gonna reabsorb a lot of water, but not a lot of salt. So the ECF is going to be hypoosmotic, and you're gonna see that as a vertical decrease in the size of the box. Okay. Now again, here we have low osmolarity here, but higher osmolarity here. Water is going to move from ECF, from the area of lower osmolarity, to the area of the higher osmolarity. And as a result of that, the ICF is going to increase. ECF is going to increase because this is what's like the volume of it is going to increase because this is the main problem here. We have an SIDH, okay? So fluid are going to move from ECF to ICF, and as a result of that, the ICF is going to increase, and the cells are going to swell as a result of that. Going back to the picture again. Hypotonic solution, less osmolarity outside. Water is going to move from outside to the inside of the cells, and therefore cells are going to swell. Going back to hypoosmotic volume expansion, now we're going to see a decrease in RBC count and in protein concentration, such like in any volume expansion, but now hematocrit is going to stay the same. Why is that going to happen? It is meant to decrease in this case, right? But because the cells are swollen, they are larger, it will appear as if they have as if the hematocrit is normal, okay? And that's why in hypoosmotic volume expansion, we're gonna have a normal hematocrit, although it should appear lower, okay? Also, you're gonna have your increase in fluid pressure. Now this is a summary slide. I took this table from Dr. Angelica's lecture, but I kind of rearranged the arrows because they were kind of messy. And I'm gonna give you some hints that you can help you, inshallah, when you get a question about them, whether about the graphs or about the arrows themselves. Okay. Starting off with extracellular fluid volume. So this is very easy. When you have a volume contraction, any type of volume contraction, you're going to have a lower extracellular volume. And when you have any type of volume expansion, you're going to have an increase in extracellular volume. Simple, okay? Easy. Any contraction, decrease in extracellular volume. Any expansion, increase in extracellular fluid volume. What about intracellular fluid volume? Remember the rule that I first said in my first slide? Uh, in my first slide about the graphs is that when you have any isoosmotic, whether it was contraction or expansion, there's not going to be any change in ICF. And that's it. There's no change in ICF in any case of isoosmotic contraction or expansion. I also said that when you have a hyperosmotic uh, ECF, hyperosmotic, are gonna have what? Are gonna have a decrease in ICF. Why is that? Because the fluid are going to move from inside of the cells to outside of the cells, from the areas of the lower osmolarity to the areas of the higher osmolarity. Okay, that's why in any hyperosmotic contraction or expansion, you're gonna have a decrease in ICF. If the opposite goes for hypoosmotic contractions, now fluid is going to move from outside the cells to inside the cells, okay? And that you're going to have an increase in any type of hypoosmotic shift. You're going to have an increase in ICF volume. Osmolarity is very, very easy. It basically depends on the name. You just need to know the type of the shift, and you can know what happens to the osmolarity. So in any isoosmotic, it's not going to change. In any hyperosmotic, it's going to increase, and in any hypoosmotic, it's going to decrease. I'm gonna jump over hematocrit to the plasma because it's gonna be easier to grasp. Again, I mentioned this example multiple times, which is about the tablespoon of sugar in the cup of tea. In any contraction, this same tablespoon spoon of sugar is going to appear as if it is more, okay? And in any expansion or dilution is going to appear as if it is less. That's the case here. Proteins are going to appear as if they are more when you have less fluids around them, and they're going to appear less when you have more fluids around them. But what about hematocrit? Initially, you would think that the same thing as protein would go, and initially that's right. So in any contraction, you would expect the hematocrit to increase. It's going to appear as if you have more cells. And in any expansion, you would expect them to decrease and have less, appear as if they are less, okay? But as I said, there are two exceptions, which are the hyperosmotic volume contraction. And in this case, in hyperosmotic volume contraction, the water is going to move from the inside to the cells to the outside of the cells, causing these cells to shrink. And because they are shrunk, now it would appear as if they have normal hematocrit. Okay. The same for hyposmotic volume expansion, but this time the cells are going to swell. Okay. Because water is going to move from outside to inside, they are going to swell, and they won't appear less, they would appear as if they are the normal amount. Okay. This is everything about this lecture. I have a couple of questions at the end, and inshallah I'm going to be explaining them. First question is, which diagram represents the changes of ICF and ECF and osmolarity in a patient with a SIADH? Okay, so the changes are shown as the dotted line here. Okay, so make sure just make sure you know that. Um, if you know what SIADH does, what type of shift it does, that's good for you. You need to know that for the exam, of course. But for now, if you don't know, I'm gonna help you with the type of shift it causes, and you wanna try to know what type of what graph it's gonna show up. So SIADH causes hypoosmotic volume expansion. Okay, it causes hypoosmotic volume expansion. Here, take a couple of seconds to try to think about it. Feel free to pause the recording. The answer here is going to be B. Okay, going back to the hypoosmotic volume expansion. This is the normal state. So in this case, you're gonna have an increase in volume of the ECF. So it's going to go wider. The ECF is going to go wider, and it's hypoosmotic, so it's going to go lower. Uh, you can basically just solve the question based on what I said right now, but I'm going to go further in explanation. Okay. Um, so because now this is hypoosmotic, the water is going to move from outside the cells to inside the cells. And you're going to have an increase in the volume of the ICF too. And you can also see that on the graph. Okay. So first of all, try to know to think, is it hypoosmotic or hyperosmotic? Once you see hypoosmotic, just eliminate all the graphs that go up. Okay. If the question is hypoosmotic, of course. So in this case, the question is a hypoosmotic. So once you see a graph that's going up against the osmolarity that is actually in the question, just cancel those answers. Okay, and then see, is it an expansion or a contraction? As you can see here, it's a expansion, and you can easily solve that. Okay. Moving on to question number two. This is an example of a guy who had severe central diabetes insipidus. You don't need to know central, but diabetes insipidus. If you know what diabetes insipidus does, try to solve it on your own. But what does diabetes insipidus do is that it's going to cause a hyperosmotic volume contraction. Okay, and I want you to think, how would that look like on that graph? Okay, so the answer of this question is going to be D. Again, it causes hypoosmotic. So you can just eliminate B and A because, sorry, it causes hyperosmotic. Okay, so you can just eliminate B and A because they are hypoosmotic and isoosmotic. So you are left with C and D. And it causes volume contraction. And as you can see here, C is just an increase in volume, while D is a decrease in volume. This is basically how you can solve it without understanding anything except the type of the shift. But for the explanation, for the sake of completion, you have again hyperosmotic. So there's an increase in osmolarity in the extracellular fluid, and as you can see, there's a vertical increase in the size of the box. Now, because osmolarity here is higher than here, water is going to move from inside the cells to outside the cells. And as you can see, there would be also a decrease in the volume of intracellular fluid. Okay. Last question. Which diagram represents the change in ECF ICF in a patient who lost 1 liter of blood after getting shot? So that guy got shot and he lost 1 liter of blood. What change are you going to see on the graph? Again, if you know what type of shift is that, you can solve the question on your own. But for the sake of your help, when you are losing pure blood or bleeding, this is an isotonic contraction of volume. Okay. So in this case, the answer is going to be A. Again, it's an isoosmotic. Isoosmotic. So the osmolarity is the same. You can just solve it based on that. Okay. But moving on, it's isoosmotic. It's contraction. So there's a decrease in the box in the size of the extracellular fluid. Okay. And again, because it's isoosmotic, as I told you at the beginning, there's going to be no change on intracellular fluid. And that's how you can come up with the answer A. So this is everything I have for this session. Please make sure to scan this QR code and share your feedback. And thank you for listening. And again, since this is a recorded session, if you have any questions, please do not hesitate to contact me at any time. I will be more than happy to help you with any questions you have. And again, no question is a bad question. Make sure you understand everything because you don't know what you can get asked on the exam. I wish you the best of luck and thank you.